presented in this figure in the different heights, 0.5 micrometer and 1 micrometer. These both are free floating trumpet arrays. Methodologically, the trumpet arrays are generated by deforming the side walls of optimized nanopillar arrays. In contrast to the nanopillar array spectra, the trumpet array spectra exhibit strong spectral absorption. We can see here the absorption peaks in both figures. Naturally, the strong absorption peaks at near infrared, which means beyond 700 nanometer from the visible to near area in the both figures. At 880 nanometer, the trumpet array absorption is around 13.5% more as compared to the nanopillar array. And at 960 nanometer is 15 times have higher absorption in as comparison to the nanopillar array. The inset in figure 1C represents the weighted absorption efficiency, which is a relative absorption spectrum weighted with the solar spectrum AM 1.5G. The transition from thin film to nanopillar array is around have a weighted absorption efficiency enhancement around 30%, and from nanopillar to the trumpet array also showed around 30% enhancement for both the arrays. From thin film to trumpet array is around twice, just twice have a higher absorption. Next, figure A to C presents the color map showing the dependency of trumpet array absorptivity spectra on bottom diameter for array height of 0.5 micron, 1 micron, and 2 micron. So here 400 nanometer represents to the nanopillar array, and 100 and 300, 200, and 100 shows the bottom diameter of the trumpet arrays. By looking, and on the right hand side is the weighted absorption efficiency plot. Interestingly, for the array height of 0.5 micron and 1 micron, weighted absorption efficiency demonstrates an almost monotonous increase with increasing the bottom diameter, with an weighted absorption efficiency increase of 35% and 20% for the nanopillar array for height of 1 micron and 0.5 micron respectively. Figure 2D presents the power flux density, which is a time average Poynting vector of two strong absorption peaks, which is presented here at 200 nanometer and 300 nanometer for the wavelength 660 nanometer. Note that the optical coupling between the adjacent nanopillar arrays is relatively weak. The optical coupling behavior in the adjacent trumpet arrays, more complex behavior we can see here. For bottom diameter of 200 nanometer, this is the trumpet top is excited. And for the bottom diameter for 300 nanometer, the bottom part of the light funnel is excited. Figure 2E presents the absorbed photon density distribution corresponding to the PFD distribution just above in figure as shown in figure 2D, where the stronger absorption in both trumpet array is evident as compared with the nanopillar array. Finally, it is noticeable that the strong excitation implies the area of high absorption efficiency. Note the high absorption efficiency at trumpet top parts and bottom part of the 200 and 300 nanometer respectively. Next, we have reflectivity and transmitivity spectra. Figure A to C shows the presents the color map showing the dependency of trumpet arrays, reflectivity spectra, and transmitivity spectra on bottom diameter for array height of 0.5 micron, 1 micron, and 2 micron. The topmost row of each color map presents the reflectivity and transmitivity spectra for nanopillar array. Interestingly, the reflectivity is lower for nanopillar arrays, and once the bottom diameter decreases, here this is the nanopillar array having a very low reflectivity, and once we are decreasing the bottom diameter, the reflectivity is also increasing. And in same manner, whenever we are decreasing the bottom diameter, deforming our nanopillar to the trumpet array, so the transmittivity increases. So as a conclusion, for all the figures, we can see this. As a conclusion, we can conclude that the nanopillar array behaves like as an anti-reflection layer, while the trumpet array behaves like as an anti-transmission layer. Next, trumpet NLC summary findings. Absorption reaches towards Yablonovich limit. Weighted absorption efficiency enhancement around 26.5% for trumpet arrays in comparison to nanopillar array. Trumpet array as an anti-transmission layer. Trumpet arrays, nanopillar array as an anti-reflection layer. And excitation of trumpet NC geometries. These are few publications based on my research work. Thank you to all, and all the calculations are done in the synopsis TCAD. And if you have any question, you can ask me, or you can just write me a mail. Thank you.
Okay, thank you, Ashish.
Thank you.
Anyone from the audience has any question? Please raise your hand if you do. Okay, so I have a few questions.
Okay.
First of all, maybe I'm not familiar with this subject, but why is the trumpet shape so important?
Actually, you saw, I think, in compound parabolic concentrators. These are very big concentrators in size, like for light trapping, for solar cell. There is some mirror in Sedebuker when you go from Beersheba to Sedebuker. So there is a concentrator
Mm-hmm.
for the silicon solar cells.
Mm-hmm. So
So
it's
so
already implemented. It's
yes,
the
it's
trumpets are already
yes,
implemented in
it's
solar cell.
implemented in very large scale. Means the dimensions is around 1 meter or half a meter in feet. But
But you.
but
Mm-hmm.
we are doing in nanoscale, Rizman.
Mm-hmm. I understand. Okay. And if I understand it correctly, so your whole research is only based on calculations and simulations?
Not we are doing experiments also in
Mm-hmm.
carry 5000 to measure absorption, basically reflection, because
Mm-hmm.
we have a substrate very thick. So transmission is zero. So basically we measure reflection, and we can subtract, and then we got absorption efficiency enhancement.
I
And
see.
our research group also doing means experimental with the near field spectroscopy. I'm also involved in that, and yes,
Mm-hmm.
we are also fabricating these type of nanopillar array in the nano fabrication at BGU. So we did
Mm.
these things. Yes,
Mm-hmm. So it's combined, like you have
yes,
both the
yes,
experimental side and the
yes,
theoretical side.
yes. I showed just numerical calculations because
Yeah,
when
that I saw. That's why I
yeah,
wanted to ask if it also works
yes.
experimentally.
Actually we
Okay.
did not develop trumpet arrays experimentally, but we are able to develop nanopillar array and light funnel arrays.
Okay. And
Okay.
last question.
Yeah.
So, what prevents you from actually taking this knowledge and fabricating a real solar cell?
Silicon, the material. Sorry, I didn't understand your question.
My question is, if you can take your results, like the diameter of the trumpets and how the photons are concentrated in them, if you can implement it now on a real life solar cell.
Yes, we can implement this in real life, and even in the laboratory in the world, means in US, in European countries, Germany, UK. They have successfully shown a very large group from Harry Atwater, Yablonovich, Eli Yablonovich. They are professors that they are able to show this nanowire in the lab. But in the point of view from the large scale fabrication, it's very costly. That's why the companies are basically going with the thin film. not with the nanowires, but I hope that very soon companies will switch to the nanowires. Even they are also developing means peroxide solar cells, means and organic solar cells, roll to roll, sheet to sheet. They want to just polish the walls of the with some polymers text, and they want to create energy. Recently in Switzerland, these things is in news that they want to be fully electrify the Switzerland country through the natural solar light with the help of um, solar cells.
Okay, I see.
Yes.
Thank you for answering my questions and for your talk.
Yeah, thank you
Is
very much, Aris.
So our next speaker is Naga Prasad. I'm really sorry if I pronounce it wrong.
Yeah, that's perfect.
Okay, from Bar Ilan University. So I made you a co-host. You can share your screen.
Thank you. Are you able to see? Yes.
Yes.
Good afternoon. Today I'm going to present my research work titled as Approaches for Controlling the Mechanism of Molecular Catalyst towards Oxygen Reaction. I'm working with Professor Ilya Greenberg's research group here. I'm working on electrocatalytic activities of carols and then small molecular complexes. What is electrocatalyst? Electrocatalyst is a catalyst that participates in electrochemical reactions in which chemical energy transforms to electrical energy. In the electrocatalytic process, the key reactions are oxygen reduction reaction, oxygen evolution reaction, hydrogen evolution reaction, hydrogen oxidation reaction, etc. In all this, oxygen reduction reaction is one of the heart of the many such fuel cells and metal air batteries devices, and it has a special importance in the electrocatalysis. So fuel cells works like batteries, but they do not run down or need any recharging as long as the fuel is supplied. So these fuel cells are various types has been identified. In all these, uh, the fuel which are going to feed at anode and then cathode and the migrating ions, except this, the rest of the mechanism is very similar in all these various types of fuel cells. In this, the mainly are proton exchange membrane fuel cells, anion exchange membrane fuel cells, direct methanol fuel cells, and phosphoric acid fuel cells, etc. So let us see what is the mechanism of a fuel cell. Here we can see a schematic picture of proton exchange membrane fuel cells. It consists anode, negative electrode, and then cathode, positive electrode, and an electrolytic solution which is sandwiched in between the two electrodes. So in the presence of catalyst, H2 transform to protons and then electrons. These protons transform from anode to cathode, and the electrons also transfer from anode to cathode through the external circuit. All these combine with the oxygen and then produce water and heat. In the anion exchange membrane fuel cells, it's also very similar with proton exchange membrane fuel cells. At anode, they are going to feed hydrogen and then cathode H2 and then water and then H2O. So oxygen and then H2O. So in this oxygen and then H2O combines and then produces hydroxide ions. These hydroxide ions migrate from cathode to anode and then interact with protons and then electrons, produces water and heat. So oxygen reduction reaction electrocatalysts are broadly divided into four categories, which are precious group metal catalysts, which are platinum group metal catalysts, and non-precious group metal catalysts, single atom metal catalysts, and metal free catalysts. So usually oxygen reduction reaction are promoted by platinum and its allies. Due to the scarcity, high cost, CO agglomeration of platinum hinders to use in the regular process. So present study focus on PGM free electrolytic catalyst, which having single metal molecular catalyst. This electrocatalytic process in acidic media proceeds two pathways, which is 4 electron pathway and 2 electron pathway. Here we can see oxygen combines with two two hydrogens means we can consider it as 4 protons and then 4 electrons. So it combines with 4 protons and then 4 electrons produce water. In the presence of 2 electron mechanism, oxygen combines with 2 protons and then 2 electrons produce hydrogen peroxide. This hydrogen peroxide is less favorable in the energy production, and its high reactivity is leads to fuel cell degradation. So the most desirable 4 electron pathway we are going to discuss here. We considered here the compression hydrogen electrode. In this mechanism, it proceeds in the 3 intermediate steps. Let us see what are the intermediate steps. Here star is catalyst. It reacts O2 and then protons and then electrons produced OOH complex in the first step. So this OOH complex again interact with proton and then electron produced oxo complex and then water. Again, oxo complex combines with another proton and then electron produced hydroxy complex. This hydroxy complex again interacts with protons and then electron produced water. So in these 4 intermediate steps, we are going to study how a molecular catalyst works. Usually this oxygen and then in the presence of protons and the electron produce water. So it's having some equilibrium potential. It is obtained from the basic thermodynamic equations. So for 4 electron process, the equilibrium potential is 1.23. For 2 electron process, peroxide formation as product, the equilibrium potential is 0.695 electron volts. From hydrogen peroxide to again it formed as water. So equilibrium potential is 1.763. Let us see how it helps in the compression hydrogen electrode approach. It is a free energy diagram for the associative pathway for platinum 111 surface using the compression hydrogen electron model. This is the initial step. It combines with oxygen and then 4 protons and then 4 electrons here. So once it interacts with the 1 proton and then 1 electron each step, and the final product is catalyst plus product. So in the ideal case, the equilibrium potential is 1.23. So the energy gap between the 2 intermediate steps are 1.23 electron volts. So here we have four energy barriers, 1, 2, 3, 4. So it is 4 times of 1.23. It is 4.92. So the ideal values we are taking as initial starting is 0 having energy. The 4 times of 1.23, it is 4.92 electron volts. And we are calculating the absorption energies of all these intermediate steps using the ab initio electronic structure theory. So in the presence of 0 potential, we can see the barrier, all the intermediate steps are downhill barrier. So this reaction is facile in this situation. Once we want to calculate the thermodynamics at the equilibrium potential U equal to 1.23, we need to scale the energies with respect to the minus n into 1.23 equilibrium potential values. This means this is 4 times of 1.23 becomes here where n is nothing but how many protons and then electrons we are adding in the intermediate step. So in this step we are going to add 4 protons and then 4 electrons, so it becomes 0 value. Here it scales minus 3 times of 1.23. It is 2 times of 1.23. It is 1 times of 1.23. So according to this, we calculate the all intermediate absorption energies. We can see uphill barrier here, and here also we can see observe uphill barrier. This means this reaction doesn't proceed through the a direct process. So the maximum potential where we can find the all intermediate steps are downhill barrier is 0.75, which is called the onset potential. So this onset potential is nothing but defines the electrocatalytic activity of a particular electrocatalyst. These values are in good agreement with experimental values obtained from compression hydrogen electron model. Let us see the hydrogen peroxide formation. For hydrogen peroxide formation, the equilibrium potential is 0.695. So once oxygen interacts with proton and then electron, it forms OOH complex. In this OOH complex, the ideal value is gap is 0.695. So another proton and electron combines formation peroxide. The value is another 0.695. So once we calculate the maximum potential where the all intermediate steps having downhill barrier is 0.64. It is in good agreement with experimental data. So another way of calculating the limiting potentials and electrocatalytic activities are through the volcano plots. From the Chebatiev principle, an ideal electrocatalyst is nothing but neither it interacts with the absorbent is neither too strong, neither not too weak. So this means it could have a intermediate interaction with the surface. Here I have plotted the absorption energy of OH and then limiting potential. The OH absorbs, this defines the rate determining step with respect to the OH absorption. The green color represents the rate determining step with respect to OH absorption. When we go from left to right, we can observe the decreasing OH binding strength. So which are placing top of the volcano curve means those are good electrocatalysts towards oxygen reduction reaction. Usually the idea in case of ideal catalyst, the difference between the OH and then OH complex is 2 times of 1.23. So in real case, most of the complexes observed is 3.2 to 0.2 plus or minus 0.0 electron volts. From this, we will obtain a fundamental overpotential which is 0.3 electron volts, which causes less favorable in the energy production process. This plus define the OH absorption energy with respect to oxygen and then OH absorption energies. You can see a large slope in case of oxo complex, and it is twice of the OH complex slope. This means oxo complex forms double bond with the surface, and the hydroxy and then hydroperoxide complex forms single bond with the surface. So let us go to my work. Here I studied metallocorals with the different metal centers, manganese, iron, and then cobalt complexes. L is a ligand I considered here, HCH3CF3 and imidazole complexes. We tried various level of theories, and we don't know which method is more accurate. So for method validation, we compared our data with the generalized multi-configuration method. Our values are, we can see this is underestimating, this is overestimating. So we consider these two methods for our approach for further analysis. We also check the basis set effect with plane wave basis and large basis and then small basis. It is immediately seen that small basis data is underestimating the values. So we considered with the plane wave basis and then large basis. This is the data which obtained for different metal complexes with and then without ligands. We considered water as implicit solvent. PBE functional, M6 functional, which we observed looks good when compared with the literature data. This is the data for the different ligands. So in all these cases, we more or less ligands are behaving very similar in all these complexes. This is the potential energy diagram for the cobalt corals. At E equal to 0, we can observe all the intermediate steps are downhill. Once we apply the maximum potential, where potential is downhill in all intermediate steps is calculated here. This we call as the onset potential. For Berg corol, it is 0.87 volts. This is the highest, and once we incorporate the excess ligand, we can observe decreased activities in case of the cobalt corals. This is for manganese complexes. Once we incorporate the excess ligand, we have observed in case of the manganese complexes increased activities. This means the similar behavior has been observed in case of iron complexes also. This means excess ligand is going to improve the activities in case of manganese and then iron complexes. These are the onset potentials obtained from different basis sets. So we are taking the benchmark plane wave basis set. It is clearly see that excess ligand is going to decrease the activities in case of cobalt. Excess ligand is going to increase the activities in case of manganese complexes. So manganese and then manganese complexes are more stable when compared with the iron and then cobalt complexes. So we further try to improve these activities from, we already increased from 0.37 to 0.54. So we try to further increase from 0.54 to, which is competitive with the platinum group metal catalyst. So we have tried some substituents which having acid groups. So we considered here benzoic acid, phenylacetic acid as substituents. Once we consider these type of substituents, we can see the intermediate steps, OH complex, this is oxo complex, hydroxy complex. So we can observe a strong hydrogen bonding in OH complex and then hydroxy complex. This stabilizes the intermediate and then improves the electrocatalytic activities. These are incompatible with the platinum group metal catalyst. We can see that with excess ligand, we have observed the onset potential 0.55, and with these hydrogen bond substance, we have achieved around 0.9 volts. So from this, we can implement and control the electrocatalytic activities towards oxygen reduction reaction. This is the same plot, and this data I have plotted here. It is immediately seen that phenylacetic acid is more improving the electrocatalytic activities when compared to the benzoic acid. We further studied this cobalt carrols with different substances. We are calling as CF3 carrol and orthocarrol and then paracarrol. CF3 carrol, these are the substances R1, R2, and orthocarrol, one we are taking as orthobenzoic acid, and paracarrol we are taking one parabenzoic acid. These are the onset potentials obtained from experiment. So they don't have any clues why it's behaving like this. Means this is at 0 pH, onset potentials are decreasing, and then after some pH switch, they are going to increase. They are going to change their slope. So we would like to try to explain this, why they are behaving like this in acidic and then basic media. We have calculated pKa values for this nitrogen atoms. Means nitrogen atoms can absorb protons. So we have calculated all these nitrogen atoms pKa values, and also COH acid also here in case of the ortho and then parabenzoic acid. Once we look at the pKa values, we can see CF3 carrol having very low pKa data, and then followed by orthocarrol and then paracarrol. This is nothing but the directly proportional to the electronegativity of the substance. So CF3 carrol is more electron withdrawing groups, and then followed by ortho and then paracarrols. Once we check the stability graphs obtained from the experiment, in case of these should follow the CF3, ortho, and then paracarrol, whatever the stability. So here we have observed orthocarrol is less stable than the paracarrol, because orthocarrol pKa value in case of acid we have observed large value. That's why it is less stable in case of acidic medium. The reverse order we have observed in case of the paracarrol. pH switch is nothing but before pH less than pKa, these nitrogens are protonated. So here they followed 2 electron mechanism, which is proton going forward is the rate determining step. Once pH is greater than pKa, it follows as electron step is as rate determining step. So here we have plotted the pH versus pKa, and then we have observed a linear fit in case of these carrols. This is obtained from the comprehensive studies. We have protonated all nitrogens here, and this is O2 in the presence of 4 protonation. Once we give 4 electrons also here, we can observe these hydrogens are interacting with the metal center. In the presence of O2 and then 4 protons and then 4 electrons, we have observed immediately the hydrogen peroxide has been observed. This is called the 2 electron process in case of acidic medium. So I would like to conclude this. We are successfully modified the electrocatalytic activities of these carrols by changing the metal center, by giving some excess ligand, and also by taking the hydrogen bonding substrate groups, and by taking some electron withdrawing groups. So experimentally, we don't know how complicated this is to implement, but theoretically, we have proved that this works well in if they are going to implement in future. Thank you for your time.
Okay, thank you very much.
Thank you.
Anybody from the audience has any question? Please raise your hand if you do. Okay. So I have a few questions, but
Yes, of course.
I'm an experimentalist, so maybe I'll ask questions from the experimental side.
Okay.
All these complexes can be synthesized?
Yes, yes.
Like,
These are synthesized.
it was done?
I think, yeah, this is collaboration with Lyra Elbows.
Mm-hmm. And are they all your work is based on comparing them to platinum-based catalyst, right?
Yes.
So did you think of comparing them also in terms of stability?
Stability, I don't know exactly how much stable platinum complex is, and then what I also don't know exactly in between platinum comparison. I don't know the stabilities in between these complexes. Whatever we have studied,
Yeah,
we
you
are able
showed.
to explain successfully. Yeah, the whatever the WAR activities are incomparable with the platinum group metal catalyst. Stability wise, I am not sure.
But in terms of activity, so you said it's compatible, it's
Yes.
comparable to the platinum, but did
Yes.
you also normalize it to the platinum content in the catalyst?
Don't know that experimentally exactly. I am not sure.
Okay, sorry.
Whatever they discuss with me, I know a few things. So total information, I don't know from experimental point of view.
Okay. So thank you very much. So
Thank you.
we have a bit of a longer break now because our next session, the flash talk session, starts only at 2:20. So enjoy your break.
Okay, thank you.
Bye bye.
Thanks for the
Bye.
presentations.
Thank you.